Hi, my name is Caitlyn Barrett,
My name is Derek Watson.
and we're in the second section of the Spring 2018 3D CAD and Engineering Documentation course at Embry-Riddle Aeronautical University. Today we're going to be talking about our midterm project. We will begin this presentation with an overview of the project. The objective of this project was to recreate a steam engine in CATIA based on provided part and assembly drawings. The assembly shown on the screen was one of the provided drawings, and we also had part drawings of each part that makes up this engine to work off of. The overall purpose of a steam engine is to convert steam power to rotational power. Knowing this helped the team recognize the purpose of each individual part and subassembly as they were created.
Here we have a parts list of the items that needed to be created for the assembly. I took the odd parts, Caitlyn took the even parts. However, I also took part 2 simply because it's basically a mirror part 1 with minimal changes, so it just made sense to have those parts created simultaneously. Caitlyn also took the standard parts, the standardized parts, whether the washers, the nuts, screws, and etc. She found all of those in the CATIA directory and just spliced them in.
Shown on the screen now is the Gantt chart that the team created at the very beginning of the project. A Gantt chart is a useful graphical tool which shows tasks performed against time. On the left are all of the main goals that the team worked on. These goals included completing the parts and the dimension drawings that go along with those parts, creating the subassemblies and the drawings that go along with those subassemblies, creating the full assembly and the drawings that are associated with that, and then finally completing the report, the PowerPoint, and the video. Up on the top are the dates that each of these goals was set to be done by, and the team stuck to these dates, which made the project pretty manageable.
Next, we'll discuss the parts of interest, the parts that gave us the most trouble, and the parts that were funnest to create. So here we have the parts that needed to be altered for the assembly to work. They happen to be my parts as well. The crankshaft bearing had to be increased, the size had to be increased by 0.5 millimeters as shown by the red arrow. And for the flywheel housing, the lip had to be increased from 6 to 8 millimeters. The difficulty with this was that the assembly is symmetric about an axis, so we had to ensure that it stayed symmetric even as we altered these pieces. None of the changes actually altered the structure of the parts, so they still look the exact same and they still function the exact same. We just had to extend some things to make it easier to assemble the rest of the pieces in the final assembly. Here we have two difficult parts, the hardest parts to create in the assembly. The first one, the right hand mainframe and port block, is mine. The left hand side looks basically the same except without the counterbores. Difficulties in creating this part comes from the fact that basically there are no horizontal lines in this entire piece, so you have to create an axis down the center and create one half of the piece and then mirror it. But the problem is that the piece is not perfectly symmetric about the mirroring axis. So there are two holes on the left hand side near the bottom that have to be created because it's not on the right hand side. So in the left hand mainframe block, the holes there are actually threaded, so that added a little bit of difficulty, but that wasn't too bad. And fundamentally, the center piece, the center ports, the sliding racks basically, those were extremely difficult to create because they don't really have any solid dimensions for them. You kind of have to use a PCD diameter and then model both and try to connect them as best as you can.
The hardest part for me to create was the cylinder restrainer bracket. At first glance at the provided images for this part, it looked really difficult because there are extrusions in different planes, many different cutouts, and it just looked like a very time-consuming part. After really looking into it though, I realized that there are two lines of symmetry. It is symmetrical both horizontally and vertically. So what I did was I modeled only a quarter of the piece, and then mirrored that about the horizontal axis, and then mirrored both of those by the vertical axis. This allowed pretty easy completion of this difficult part.
Next, we will discuss the subassemblies. There are 5 overall. We'll talk about each one individually and how we broke it up and why. The first subassembly is the crank plate subassembly. The subassembly is responsible for transferring the power from the piston rod to the crankshaft. Basically, that means it's responsible for keeping the structure stable as it's rotating. For this part, you can't really see the second piece, which is a pin because it's flush in the surface that you're looking at. But there are 2 pieces, the crank plate shaft, which is the longer cylindrical piece, and the pin that's connected by a press fit. For this piece, there wasn't much difficulty in creating it. The constraint is really just a regular coincidence constraint and a offset, so no big deal there. But both pieces here are made out of aluminum. There's 2 of these in the overall assembly, so you'll see them multiple times.
The next assembly that was created was the crankshaft subassembly. As seen here on the screen, this subassembly is responsible for transferring power from the crank plate to the flywheel. As you can see in the image, all of the parts that make up this assembly are also aluminum, as they were with the crank plate subassembly. This subassembly was also pretty easy to create. It's only made up of 2 unique parts, the crankshaft and then the pin. 2 pins are simply press fit into the crankshaft, and that is all that makes up this subassembly. The next subassembly created was the cylinder subassembly. This subassembly is responsible for housing the pressurized steam that powers the piston. This subassembly, it's made up of quite a few parts, 7 unique parts to be exact. They're all different various materials. The screws are made of steel, the pins and spring are made of aluminum, and then the cylindrical parts are made up of gold. I'd say that this was the hardest subassembly that we did, just simply because it had the most unique pieces to assemble together. But luckily, all the parts were made well, so the subassembly fit together well.
The next one is the piston subassembly. This is responsible for rotating the crankshaft through steam power. This one has 3 unique parts all connected together through a press fit. The parts here are seen as aluminum and gold in various spots. The most difficult aspect of this part was that the top part, the gold portion, it has a hole that goes through to let the rod in. Well, for some reason, CATIA oddly forms that hole, so you have to create a plane that basically is right at the end of the hole, and then when you create the hole command, you just say up to plane and select that plane as the end of the hole. A strange happenstance, the actual schematics that we were given don't give a few dimensions here. You can extrapolate them just by looking at the parts and how they have to fit together, but it was still a little strange that some of the things were missing.
The final subassembly that was made was the reverser subassembly. This subassembly is responsible for controlling the direction of rotation of the flywheel through governing both the input and output flow. As you can see here, this subassembly is again made up of various different materials. The reverser and the plate are both gold, as well as the pin. The reverser spring is aluminum, and then the washer and the nut are steel. This subassembly was not too difficult to create. Each part has an instance of only 1, and then each part is really assembled all along the same axis, so it was pretty easy to put together.
Alright, after all that talking, we finally get to the final assembly. Here's the final rendered image of our assembly. The pieces were made of gold fundamentally because the schematic showed a yellow color, so we took the liberty to make it gold. Some other parts were aluminum simply because it just made sense for them to be aluminum, like rods and stuff like that. Some difficulties we had in creating the final assembly was that we had some clashes due to weird dimensioning, so we had to kind of change and fix that as we went along. So basically, we started from a ground up approach. After we created our subassemblies, we started the base block and built the entire assembly from that block, one step at a time.
In conclusion, the team was able to successfully complete this project. After a lot of hard work, the assembly was able to be made with no clashing, and when you manipulate the assembly with respect to the constraints, everything moves together, which is really great. Through completing this project, the team discovered the best approach to take when tackling the final project. What really worked for our midterm project was creating the Gantt chart in the beginning of the project. This split the work evenly over the course of the project and allowed for the team to better manage their time. One thing that we think we'll improve on the final project is to divide the parts in a more logical way. As described earlier, we simply divided the parts by even and odd pairing. Sometimes this meant that some subassemblies, the parts in those subassemblies, were created by the two different team members. Next time on the final, we'll really sit down and look over the project as a whole and divide the parts by subassembly.